I would like to start with the question for this talk. Have you ever experienced a kernel crash and wondered why it happened? If so, well, we're here today to help you by introducing KRR, an efficient and scalable kernel record replay tool. We know kernel failures are severe. They take the whole machines down, all the applications are disrupted. So, diagnosing and fixing kernel failures is critically important. However, even we do have the core dump or the log message at the failure point, they still give us partial clues. Due to the high complexity of the kernel execution, the failure point could be far away from where the bug originated. This makes diagnosing kernel failures feel like finding a needle in a haystack. So the key question in this talk is that how can we help developers diagnose complex kernel bugs easily? The record replay, or called RR, is a powerful solution. During the software execution, all the external inputs are recorded into a trace file. With the trace file, we can rerun the same execution deterministically. This makes the failure repeatable and enables some useful analysis techniques, such as reverse debugging, taint analysis, and more. R is also popular. Besides abundance of research papers about it, there are also widely used tools to help developers debug software. Then the question comes to, can we apply the RR technique to the kernel? The traditional approach to do this is the whole machine RR, in which the target system, including the kernel, is running inside the VM. The hypervisor acts like a recorder, capturing all the inputs into the VM. The inputs include the interrupt, non-deterministic instruction, the I/O data, and for multi-core, it somehow records the memory access ordering between cores. However, using the whole machine RR to record the kernel execution is not efficient, especially for today's workloads. Here are two properties of the workloads that make this problem more severe. Firstly, the workloads are highly concurrent, especially on multi-core. As explained, the whole machine RR has to record the memory access ordering somehow, which introduces significant overhead to the entire system. For example, prior work presents the slowdown of 2.3 times on 2-core VM and 4.1 times on 4-core, indicating the lack of scalability with the core numbers. Secondly, the workloads are I/O intensive. As we know, the I/O input from the external devices is also part of the recording input. So the higher VM I/O, the more data needs to be recorded. On the other hand, the recording efficiency is also very important because many tricky and hard-to-catch bugs just happen in long-running systems and even in production where the performance-critical workloads are running. So our goal is to improve the efficiency for recording the kernel as much as possible. Our key idea is to reduce the record-replay boundary from whole machine to the kernel. And our work KRR records the inputs to the kernel and only replay the kernel execution. At the first glance, the reduced boundary could be helpful for improving the recording efficiency due to recording less code execution. But notice, compared with the whole machine RR, KRR actually adds one more recording interface from the user space, which could be more expensive However, despite this additional cost, there are two benefits that make this approach still significantly more efficient than traditional approach. Firstly, for concurrent workloads, even though the kernel is complex, it's usually not the most often running code on a given core. In many workloads, the user space takes the majority of the CPU time. By reducing the boundary to the kernel, we don't have to record the user space concurrency non-determinism. Secondly, for the I/O-intensive applications, the kernel bypass I/O has been the trend in today's data center. In such workloads, a bulk of the I/O input is directly handled by the user space without kernel involvement. So reducing the boundary to the kernel can help us avoid recording such type of input. Now we know the potential benefits of this approach. To achieve such design, we have to address two major challenges first. The challenge one is to record the user space inputs. The challenge two is to record the multi-core system. And what makes it more challenging is that how do we do both of them in a more efficient way than traditional approaches? So let's talk about challenge one. Since we have to record the user space inputs to the kernel, if we just naively trap each of them from the hypervisor, then there could be tons of VM exits introduced, which are very expensive and break the whole point of recording efficiency. How do we deal with it? The KRR solution is to introduce a split recorder design. The first part of the recorder, just like the whole machine RR, sits in the hypervisor, intercepting the inputs from the hypervisor to the kernel, such as interrupt, I/O data, non-deterministic instructions. And the second part of the recorder runs inside the guest kernel, intercepting the inputs from the user space. There are explicit inputs such as system call, exceptions, memory accesses to the user space buffer, and there are also implicit inputs such as page table updates caused by the user space. Since this recorder is running inside the VM, there is no additional VM exits introduced for recording such inputs. Together, these two inputs collaboratively log these two recorders collaboratively log the inputs to a shared event trace. And our synchronization mechanism ensures that all the events are correctly ordered. Now let's talk about the challenge two. In multi-core system, since we could have multiple threads running on different cores, if they just access to the same memory address concurrently, then this execution could be non-deterministic. Then how could we ensure the correct replay? A commonly used approach to address this problem is to constrain the parallelism. And one specific technique is to serialize the execution by allowing only one core to run at a time. This makes the memory accesses deterministic with a repeatable order. However, if this is applied to the whole system in our approach, the user space would also suffer significant overhead. Then how do we deal with this problem? The KRR solution is to only serialize the kernel execution. Let's walk through an example. Suppose there are two cores running in the user space. The KRR allows them to run in parallel. However, if they try to get into the kernel mode at the same time, KRR only ensures one core can run in the kernel mode at a time. In this case, core 0 runs first, and core 1 has to wait until core 0 finishes its kernel execution, and core 1 can continue to execute. And in this workflow, we can notice that the KRR still preserves the parallelism between the user space executions, or the parallelism between the user space execution and kernel space execution. On the other hand, it only serialized the kernel execution for determinism. While using the serialization technique, for user space intensive workloads, the serialization of overhead could be reduced. Now, let's put everything together. In KRR, there are two recorders. One is running in the hypervisor. The other one is running the guest kernel. They collaboratively record the kernel inputs into a shared event trace. In the multi-core system, the KRR applies the fine-grained serialization to the kernel execution only, while still preserving the user space parallelism. We also verify the KRR's replay correctness by running over 8,000 test cases from Linux test project, and KRR was able to pass all of them. Okay, now we're going to jump into the evaluation part. The first question is that, how is KRR's recording scalability? In this part, we measured the recording slowdown of KRR and whole machine RR running the RocksDB benchmarks. To make a fair comparison, we implement the whole machine RR prototype using the same QEMU and KVM version as KRR does, based on existing approaches. And here is the average slowdown factor across different benchmarks from 1 core to 32 cores. The results show that the KRR can scale well to multi-core system. On multi-core system, the KRR is from 2.7 times to 44 times faster than whole machine RR. We also observed significant improvements of KRR in Linux compilation workloads. The next question is, can KRR efficiency be benefited by the kernel bypass workloads? In this part, we measure the KRR slowdown when running the RocksDB with the kernel bypass and kernel I/O in a 2-core VM. And here is the KRR slowdown factor across 4 typical workloads. And from the results, we can see, for the most of the cases, the KRR in the kernel bypass could be more than 15% faster than KRR in the kernel I/O, which indicates that KRR could be even more efficient under kernel bypass workloads. The last, but the most important question is that, can KRR effectively record complex kernel bugs? In this part, we run totally 17 kernel bugs from 13 different kernel versions on KRR. And 12 of them are random bugs from Sysbot, including 6 non-deterministic bugs, which require specific thread interleaving or interrupt timing to be triggered. We also run another 5 high-risk CVEs. The results show that KRR was able to record 16 out of the 17. The one left requires the parallelism among multiple cores in the kernel mode, which is prevented by KRR's serialization approach. And for more technical details, please check out our paper. Here are the final takeaways of KRR. It is the first RR framework targeting the kernel boundary. It is also very efficient and scalable with the multi-core support. It can record and replay real-world complex bugs. It's open source. And one last thing, record once, debug anytime. Thank you. I'm happy to take questions.